So yeah, thank you very much for coming. So this is sort of the accumulation of several months of work setting up the challenge, and then everyone participating, and now we're sort of presenting the sort of top 5 teams. But before I start, I just want to say a big thank you to everybody, all the teams who are presenting today. And also everyone else who participated. I know it takes a lot of time out. We were doing weekly challenges every, it was every other week and then every week, so it's a lot of people's time. So we really do appreciate it, and I think we got a lot of value out of it. So what I'm going to do is I'm going to start just a bit of housekeeping. So we're going to be recording this event, so we'll be sharing that later. If there's any edits by any of the speakers, then let us know. We can do that. But also we'll try and share that on our YouTube as soon as we can after this event. I'm going to do a quick presentation, and then we'll get on with the actual main speakers. The rule will be we'll have a couple of questions after the end of each talk, so we'll save those till the end. So the plan for that will be, if you want to ask a question live, just put your hand up using the button above, or you can sort of just write and I'll read them out, and then we'll move on to the next speaker. If there's any more questions, we can probably leave it to the end of the event, and then I'll also probably partake in that and answer some questions. So, right, without further ado, let me try and share my slides. So can you see? Yeah, let me know if you can't see those slides. So I'm just going to very quickly overview the project, so then we can get on with the actual presentations. Yeah. So this is what the data science challenge is one work package from the presumed open data project. This was an NAA project run by Western Power Distribution, who are a major distribution network operator here in the UK. And we also worked with the Centre for Sustainable Energy, who developed the hub where the data was stored. And there was really 2 aims for the project. It was to increase the visibility of data, and it was also to demonstrate the value in making that data open and more accessible. So the challenge was quite simple, really, in terms of stating, at least, maybe not so much in terms of solving. We have a big battery connected to the distribution network. It's next to a distribution substation, primary substation, and next to it we've also connected to a 5 megawatt solar farm. These are all in Devon in southwest England, and there's a map in the top right there showing the location. And the task was to design a schedule a week ahead of knowing what the actual demand and solar would be, to design a schedule, discharging and discharging schedule for the battery, which would maximize the peak reduction you can get in the evening, and we define the evening to be sort of from 3:30 p.m. to 9 p.m., but also utilizing as much solar photovoltaic energy as you can during the day, so using as much renewables as we could. As well as providing the historical data, we provided some essentially weather forecasts, although they were actually reanalysis, from multiple grid points close to the site, and you can see 4 of them in the map on the right as well. And so we implemented this over about 7 weeks. We had 1 practice challenge, which really was useful in trying to iron out some of the details, make sure everything was clearly conveyed and everyone understood how to submit. And then we had 4 weekly tasks, essentially weekly tasks. And then the prizes, we offered some prizes as well, which would be a publication, which I'm happy to hear that several people will be publishing their results, especially some of the speakers today, and then an ideas pitch. I will not go into detail here, but this is just showing you the evening period. These are daily profiles for the demand and the PV. So as well as showing the evening slot, it's also showing you the uncertainty there. There's a lot of variability, so it's not a simple challenge. And on top of that as well, you have to make sure you satisfy the battery constraints. So ultimately, it's a constrained optimization under uncertainty, if you want to sort of be technical about that. But I mean, if you've read the information pack we gave out, this is all in there, and several of the talks will also be going into this. The scoring, again, I'll just very quickly here, it was split into 2 core elements, again, related to the demand and the regeneration. The first aspect, the core aspect of the scoring, was the peak reduction, which we measured as a percentage. And we also weighted that according to how much energy used from the solar. And the weighting of that was based on, essentially a lifetime greenhouse gas emissions. There's other ways to do it, of course, but this seems sort of like a nice way to do it statically, maybe rather than looking at prices. Yeah, and then for each week, we just average those scores, and that gives you that weekly score. Just a very quick, this is the naive benchmark, so last week is this week. This shows you what happens. This is the original profile in black. And once you've implemented your storage device, what's the new demand on the grid is in red. So sometimes when there's a lot of solar, these are the solar profiles for each day, you can just reduce the peak quite well using most of the solar. But on some days, there's not so much. And actually, you could possibly increase the peak, the daily peak on there. So there's obviously some design issues which you could say we could change anything, but for our purposes, it was good to just sort of simplify the task and have it as 2 split periods. As I said, the participation was great. We advertised across a whole the teams, our own team and WPD and Tabitha, who's online now. We really thank her for helping spread some of this and advertise some of this challenge. We also went through a few major newsletters and groups, so you may find those interesting to join into as well. And we had great participation. 365 individuals registered for our kickoff event, and many of them came on to be participating. So we had about 55 teams in total. And what was great about that was that there was very little dropout. I've been involved in some challenges before, and at the end there's quite a few. So I really appreciate everyone putting the time and effort into this challenge. And also, it was very much a worldwide challenge. We had 15 different countries were involved in this. Lots of different organizations. We had universities. I've said 30 different ones of those. We had consultancies. We had big industrial bodies in energy networks. So it was really a great diversity of participation. Yeah, and also in terms of I'm just going to talk generally here because everyone's going to talk about maybe their individual results later. One thing that was great was there was really a good improvement from one task to the next. So this wasn't mainly just because people were dropping out who were maybe scoring more poorly. There was a lot of improvement as people got more experience with the data. They learned various things, and in some cases just found a method that really worked for them. So what we've got here is a comparison to the benchmark. You get an improvement, whereas by the end of the challenge, 2/3 of the teams were outscoring the benchmark. And on the bottom here, what we have is the bottom left here is the spread of the scores. So we're going from from task 0, the practice 1, to the 4th task, and you can see there's a funneling here as people get better and better with that. And the final thing I want to just say about scoring is that we split this. I had a look at these scores in terms of the 2 components, the peak reduction, and that you can see that on the y-axis, and on the x-axis you can see how much they charged with PV. So the average scores, at least across all the tasks. And one thing was the main part of the score was obviously reducing the peak, but the second part of the score was also about the PV, and you had to do well on both of those. I mean, it was possibly more important to actually manage the peak reduction, but if you wanted to be in the top scores, then actually you had to have a decent score as well for the PV, although perhaps not as strongly as you would with the peak. So this is my last points before we get on with the talks. As I said, the participation, I think, is evidence that there's a lot of interest and there's a lot of value by making that data available. And that's something we want to keep doing. The Energy Systems Catapult, we want to encourage that because it really drives the innovation we're seeing. Another interesting point here is that you're going to see a big variety of different talks. I think this is a really good, it's a rare you get to see and compare different methods, how people look at a problem, how they utilize the data, the different features of extraction on the same problem. Very rarely you can get that comparison, which I think is really great. But it also means we've got a really good source here for seeing what are decent benchmarks and state of the art. One of the issues we see with both the academic literature and things you can apply in operational is it's very hard to see the comparisons against a state of the art. So I think this is really valuable. And finally, although we've sort of got the top 5 here, they all did really well, and there's a very close scoring between all of them. And I think that sort of indicates there's several ways to sort of achieve a really good results. There's never always a perfect method or approach, which will, which you can always choose. So I think that's really interesting, and it might fit different use cases, and for different businesses, it might be suitable for one method rather than another. That's all I wanted to say now. So I'd like to actually, I will not share, so I'll let them share their slides directly. So without further ado, let me stop sharing. Yeah. So yeah, I'd like to introduce the first team, which is Titan. So these came 5th in the competition. The team's Titans. Gergő Barta is going to share his slides, and he works for Utopus Insights. So take it away.
Awesome. Thank you, Steve. Hope I am loud and clear, and you guys can see my screen as well.
Yep, I can see it.
Awesome. Thank you. So yeah, welcome everyone. We are Team Titans, and today I want to introduce you to our methodology and our overall experience in the POD challenge. My name is Gergő, and together with my Benedek, I will guide you through our journey. So who is Team Titans? We are a mixed team of data scientists from various backgrounds and various nationalities. The common factor between us is that we are working, or at one point have worked, for a company called Utopus Insights. So who is Utopus Insights? Utopus Insights is a global company, and our aim is to bring the next generation of energy analytics to the industry, and also to completely digitalize the energy industry. So this is an ambitious goal, and obviously the POD challenge was of high interest to us. So we decided to enter the challenge, and we split the original problem into 3 sub-problems and assigned team members to each problem, as you can see. So the original problem is a battery charge scheduling, and obviously the output of that is clear. We need to provide a schedule of half-hourly charge-discharge rates, and we wanted to approach that using a constraint optimization. The constraints here are quite clear: the capacity of the battery and the charging rate of the battery. And obviously, we need to provide solar forecasting and demand forecasting for that. What we decided to do is to go with deterministic forecasting in this case. And since we received a lot of historical data from the competition organizers, we approached it with a machine learning based solution based on the historical data. Now, why we chose to provide deterministic forecasts instead of probabilistic forecasts here. So basically, this is a competition, and accuracy wins competitions. So we wanted the most accurate forecasts to be fed into the scheduler, and we did not want to limit our tool set to probabilistic approaches, but wanted to incorporate the most accurate deterministic ones. And we decided to tackle the uncertainty in the system through the battery charge scheduler instead. The scheduler was created using Julia, and the forecasting engines were written in Python. Sorry about that, that's my dog. Yeah, so the challenge was done through 4 rounds and 1 practice round. So the practice round was a bit easy because it was not real yet. There were no high stakes, but also a bit difficult because of the lack of historical data. At this point, we did not have an entire year worth of data yet. So that was a bit problematic. So instead we went for a simple solution, and wanted to build our pipelines and prove the concept that we have put together. So let me start by describing the demand forecasting engine for the round 0. Basically, it was the input data was simple data attributes, some UK holidays. We all know it's very important for demand forecasting. We implemented a weather station selection regime where we only incorporated part of the weather data provided by the organizers and built on the top a simple random forest regressor. Let's go over to the solar forecasting side, and if Benedek, you can unmute yourself, then I can give you the floor.
Yeah, I'm here. So in the round 0, we utilized no, you can perhaps continue sharing your screen. So we utilized the 0 round to do an extensive EDA and understand really the data we have, and we focused on building the pipeline itself, as Gergő mentioned, so that the later rounds were easy to basically re-implement whatever we had. So the error metric which we utilized for solar forecasting was normalized mean absolute error. So we divided the mean absolute error by the capacity of the power plant. And in the initial stage, we basically just went with the most simple algorithms with all the NWP, so numerical weather prediction data. The only challenge which was there, and we had to implement a routine to do that, is how to interpolate the hourly irradiance data to half an hour granularity, which was required for the battery scheduler. And for that, we got the permission to utilize PV libraries. So we established the clear sky curves for the irradiance, and hence we were able to provide a better interpolation algorithm than any kind of other linear or spline-based interpolation algo.
Awesome, thanks, Benedek. So basically, we took the point forecasts provided by the solar forecasting engine and the demand forecasting engine and fed them into the battery scheduler. In this round, the battery scheduler was a simple scheduler that actually took the point forecasts as face value. So we assumed no error in these forecasts. There was one trick that we assigned some extra weights, prioritizing midday hours in terms of solar charging of the battery. So as I mentioned, we did not really aim at accuracy at this point, and the results validated this. We got a peak reduction score of 100, lagging behind the round winner, and this was enough for rank 9 in this round. But obviously, the real challenge started in round 1, which was a full period, and it still meant we did not have an entire year worth of data, so that was a key challenge here. But since the stakes were higher this time, we really wanted to give more sophisticated approaches. Let me start with the demand forecasting side. We added a lot of new features data-wise. For instance, we changed to a more natural cyclical representation of date variables. We discarded the weather station selection and went with a more robust averaging of temperature and irradiance values. We added a lot of features on top of those values, like lagged values and rolling window values. We added heating degree days and some interaction variables as well. And I would like to highlight one key aspect of our solution, which is that we basically took the output of the solar forecasting engine and fed it not only to the battery charge scheduler, but the demand forecasting itself. The reason for this is that in this particular area of the UK, rooftop solar is booming, and we all know that this affects demand, at least from the residential side of it, as negative demand. And we wanted to find a way to incorporate this information. And the relationship or the assumption is quite loose. The relationship is loose between the Newton Downs solar farm and the rooftop solar in the area, but it was the simplest and easiest way to incorporate this negative demand into our system. So basically, what we said is let's feed the solar output into the demand forecasting, and let the models try to assess how they can extrapolate from the farm output to the rooftop output itself. So this is an on and on thing, scheme throughout the competition for us. To be honest, at this point, we found that the PV generation did not really have accuracy because of most probably because of the lack of historical data. So the solar forecasting was not mature enough, but in later stages of the competition, this really helped our accuracy. Nevertheless, you can see that we achieved a 4.8 accuracy for this round. And again, Benedek, you can tell us about the solar side.
Yeah, so in the round one, we still had few data, which was a challenge. We didn't have a full year worth of data. So to capture seasonality in the solar curves, what we did is to introduce a factor to clear sky curves for both the irradiance and the power, so that we got rid of the seasonality effect. This was one trick which we utilized here, and which gave us better results. In later runs, we had a full year worth of data, so it was not needed. Here we already introduced ensemble types of algorithms. So we utilized all kinds of different algos to stack them, and which gave us better results at the end.
Awesome. And then for the battery charge scheduler side, at this round, we already started incorporating uncertainty of the forecast, and also introduced something called an energy balance constraint, which is basically an extra constraint so that we can flatten out the net demand during the peak hours. So this helps our peak reduction score a lot. But I have to admit that at this point of the competition, there were still some bugs in the scheduler. So in the end, our solution was suboptimal. You can see that we achieved a peak reduction of 90, which was lagging behind the round winner. And to be honest, this was a fairly easy round otherwise. So we only ranked 21 with this approach. But spoiler alert, at the end, we come up to the rank of the 5th place. So let's see how we did that. So basically, the next round was a spring period time, and it was already more than 1 year worth of data. So it was easier, at least from the demand forecasting side. Not much was needed to change. As I mentioned already, we discarded the PV generation for the time being because it did not really help. The last round, at least, backtesting proved so. And we went with the same model ensemble, which was basically an equally weighted ensemble of extra trees models, XGBoost and Light GBM. This proved to be a very robust solution, and this was important throughout the competition. Again, back to you, Benedek. Tell us about the solar.
In the solar case, in the second round already, we had the established pipeline. So we introduced some interaction variables. That was all the tricks. But really here we already had more than 1 year worth of data. So that basically led to less sophisticated approaches, which were resulting in better accuracies.
Awesome. Yeah, we can see that now the NME dropped to 5.2 in case of the solar forecast. So feeding to quite accurate forecast into the battery scheduler, and also slight tuning of the battery scheduler resulted in a peak reduction score of 79.5, just barely behind the round winner. So in this round, we scored 2nd, and our overall rank increased from 21st to 13. Now, the next round was a bit tricky. It was the Christmas period, to be exact, the pre-Christmas period. And we all know that it's quite a nightmare from the demand forecasting side. In hindsight, we should have taken special care and decreased the complexity of the model, but we did not do so. There was just one modification from the previous round winning solution, is that we limited the modeling scope to the afternoon discharge hours so that the model can focus on this one. Still, the MAPE was that we achieved for 4.5 is in league with earlier MAPEs. So I think we tackled the issue well, but we could have done better from the demand side, and ultimately this showed in the final results. Any update on the solar side, Benedek?
I guess one thing which I forgot to mention in the previous round is that we introduced the biasing techniques for the irradiance variables. So we selected some grid points from the NWPs, and then we utilized a pre-modeling basically based on the measured irradiance data, historical measured irradiance data. And then we did some kind of debiasing to get more punctual irradiance forecasts. That is something which we also utilized in this round. And if you take a look at the NMAE, here we have 1.5%. In the previous rounds, it was much higher. And it's just showing the dependency on the accuracy of the NWP's forecast. Maybe that's it.
Exactly. Now we had quite accurate forecasts again, and feeding them into the scheduler, we revised a few things. Just some minor updates. Basically, what we did at this point of the competition is that we took the test datasets from previous rounds and tried to fine-tune some of the internal constraints and internal parameters that we have been using, and also added a more sophisticated weighting scheme to allow the deviation from the average demand during the peak hours, net demand. Again, this smoothed out some of the scheduling details. So the peak reduction itself is in league with the round winner, but this was a difficult round, and it was only enough for ninth place. But overall, we improved our score from 13th place to 9th place. So even that was enough for a big improvement. And this is how we turned to the last round, which is the COVID period, or it seems so, and we thought so at the beginning that we had to forecast for COVID lockdown period, which is obviously a nightmare, again, for demand forecasting. But looking closer to the data and investigating it through extensive EDA, we found that actually this is a post-lockdown period where most of the restrictions have already been lifted and the demand was almost back to normal values. So we took that information and discarded the lockdown period from our training data and focused on normal historical demand data instead. And also, since this was the last round, we already accumulated sufficient amounts of data, and we started discarding all their now obsolete data points from the training. And this resulted in a MAPE of 5.2, which is on par with previous rounds. So we can say that we have sufficiently tackled the issue of a post-lockdown period, at least from the demand perspective.
Gergő, we got about a minute, so just
Yeah, awesome, thanks. Yeah, maybe then let's skip the solar side. There were just some slight optimizations there.
Yep.
Again, the battery scheduler, just some slight fine-tuning of parameters. Again, peak reduction was really close to the round winner. We came in second, and overall we jumped from 9th place to the 5th place, as you all know it. So let's just take a look at the progress that we have made in a visual way. So basically we have the yellow dots, which are the theoretical maximum, and the blue dots, which represent the benchmark. And the round winner solution is in green, and our solution can be seen in teal. And as I have said, for the later rounds, we quite matched up with the winners. There were slight issues with the Christmas period, but for round 2 and 4, we came really close to the winners. Unfortunately, the first round was a bit messed up from our end. But what I can say is that our solution improved throughout the rounds and matured enough so that when we did a backtesting with our final battery scheduler, we have seen that we could deliver a really robust solution and a generally compared very well to the challenge winners as well. So overall, it was a great journey, a lot of lessons learned for us, and thanks for organizing it, and congratulations to the winning teams because they were even better than us. So the floor is yours, Stephen, and let's hear from the other teams.
Thank you very much for that. I'll give you a virtual applause. Yeah, do we have any questions? We've probably got time for a quick question or two. So if you want to put either your hand up or type in the chat. I do have a quick question about your. So how do you find that the collaboration worked against the three teams? Do you feel like tell us a bit more about that maybe?
Yeah, so this is something that we are quite used to, being in a global company. So Microsoft Teams and virtual teams is something that we are very, very much used to. I can say in hindsight that the information flow could have been better. So for instance, I mentioned that I think in round 3, we realized that we don't need to do good on the demand forecasting for the morning hours, because that's not of interest to us. And we could have started with the same models in the first place. So this is again something that was a lack of information flow. But otherwise, I think things went smoothly. Kudos to my team members. They really put their best effort in the entire solution.
Brilliant. Thank you very much. So yeah, shall I introduce if you have any more questions for Gergő, just ask in the chat. Oh, sorry, I think we do have one. Sorry, another question. Yeah, Ben Lend asks, what additional data would you like to have had access to?
Okay, so yeah, I've talked about this one. Rooftop solar is something that was really in the picture and was a gray area. So the models did not really have all the clues for that. So that would have been nice. And other than that, I loved the scheme of the challenge. But what I missed is direct comparability between solar and solar solutions and demand solutions. So we did not see that coming in from competitors. We only saw the final peak demand reduction score. So that was again a gray area, and we would be really interested in seeing how we competed in those sub areas.
Brilliant, thank you. Okay, thank you very much again for that talk. So the second speaker today will be the fourth team, TeamBath from Bath University. Yuanbin Zhu, if you could share your screen.
Hello.
Hello. So yeah, if you just want to share your screen and your slides. I'll give you a warning 3 minutes before the end, so I forgot to mention that at the start.
It's okay.
Yeah, I can see that. Brilliant.
Yeah. Hi everyone. I'm Yuanbin Zhu, and a student member of the TeamBath. And TeamBath is a 4-member team with Dr. Chen Honggu, Junong Li, me, and Shuangqi Li. And Dr. Chen Honggu is our supervisor. And I'm very glad to be here to present about our work on this presumed open data challenge. And in the following, I will introduce our work in 2 parts. The first part will be the forecasting model for the PV and the load with the long short-term memory, and then with the energy storage optimization models. And the first one, for our PV and load forecasting, we adapt the deep recurrent neural network to predict the PV output by analyzing its temporal features in time series. And the temporal features in the above 3 time series will be captured and mapped to the feature domains with the network structures. Which means, in other words, the long short-term memory unit will be used in our work to capture the long-term dependency in the TV output power synchronous. And as shown in the structure figure below, we set 3 gates in the long short-term units to control the information flow: the input gate, forget gate, and output gate. And for our PV prediction model, initially, we only used the long short-term memory to predict the PV output based on historical PV data. But the weather data was not used. But then we found the prediction accuracy was so unsatisfying, and so in the subsequent task, we used both the weather and the historical PV data in the prediction model. And for the load forecasting, we use a similar method to establish the load predicting model. First is the historical load data, which is strongly relevant to the target, which is the same weekdays or holidays in that year. And then to avoid overfitting the prediction result, we add some relevant information such as the solar irradiance, time, temperature to the training data sets. Then for the PV prediction models, only the historical data near the prediction period in the current years and will be used as the training data. That's because the PV output is strongly related to the seasons. And also, only the highly relevant historical load data was adapted in the load prediction model. Then we use the covariance technology to select the best parameter of validated models. And in the right figures, there's the prediction samples of the PVs and its error distributions. With the developed the deep long short-term memory prediction model, the future PV output power within 1 week can be quantified, estimated, and validate efficiency of the energy storage operation schedules. Then for the energy storage optimization models, we divided the model into 4 different components according to different operation modes and the PV output levels. With the object of fully absorb the PV during the slot 1 to 31 and shoving the peak load during the slot 32 to 42. The problem we solved is adapted the PSO, the particle sweat optimization methods. And for the first scenario, the energy storage discharging optimization model with the stable and normal PV output. We set the low satisfying and the peak reduction, which also the scored in the match, as the object. Then following the constraint with the rate of the battery charge and discharge. Then for the energy storage charging optimization model with the unstable MPV output, we build 3 weeks data sets consisting of the predict data of the target weeks and the real profile of the last 2 weeks. Then the unstable PV output period is hard to predict, but we can absorb it by the weather data. And during that period, the PV output could be higher and lower than the energy storage capacity and cannot be predicted accurately. So we combined all the unstable PV output curve in the 3-week data set to form a new curve by the linear fitting method. Then the final curve in the optimization is formed by averaging the predicting curve and the new curve. Then the third optimization model is the energy storage charging optimization with the stable but low PV output. If the predicted PV output is far lower than the energy storage capacities, the charging strategy is to set the energy storage charging schedule fully cover the PV output during the target period. To realize that, the predicted PV output is put into the optimization model after being proportionally increased and add with the constant increment. then the amount of the modified PV output is equal to energy storage capacity. The last one, the energy storage charging optimization with stable and high PV output. Since the PV output is very high and much higher than energy storage capacity, so in that scenario, the charging strategy for the energy storage is aimed to absorb the lowest PV output for each time slot in the day with the stable and high PV output in the 3-week data sets. And that's all for my presentation. Thank you for listening.
Brilliant. Thank you very much. Is there any questions, Yuanbin? In the chat again, or we have Rodoy. Yeah, please go ahead.
Hi. Thanks for the presentation. It was really good. Was just wondering if you could explain a bit better the objective functions, maybe or the optimization, with the energy storage optimization. That would be really helpful. Quickly, time permitting. Thank you.
I don't think we can hear you very well.
Hi, do you mean this
objective
function?
Yeah.
Actually, it's peak reduction and the low satisfying, and these two is partly provided by the batch challenge. So it's actually a certain target. I think it's not some brilliant things.
Yeah, just quickly follow up on that one. That because I see the max operator there, so I was wondering just what sort of method has been used here. Is it constraint optimization, convex, non-convex?
Yeah, here is I think I should find a variable for you. Sorry, I can't find.
No worries, I can maybe reach out later. Thank you.
It's a little bit hard for me to explain that because I'm not responsible for the that part.
Fine.
If you
fine.
want
Later. Thank you very much.
Yeah.
Thank you.
There's another question from Sam Hinton. Asking about the LSTM networks. Can you quantify how they performed compared to simpler models such as basic linear regression or ARX models? I guess an extension that I would like to ask is, yeah, maybe about the computational cost of those.
What do you mean?
How do you think the LSTM models performed to some more simpler methods? Did you compare them to sort of linear regression models or autoregressive models?
Yes, we did. Actually, we had do a simple test in the first task, and we found because the load profile and PV profile has strong temporal features, so we found the long short-term memory method has the was the best for this scenario, this matching challenge scenario.
Okay, brilliant. Yeah, there's one more question from Day about the data resolution. Say quickly about what the resolution of the data you used was.
The resolution data is zip into each hour, half an hour of half an hour.
Brilliant. Okay, thank you. So we're going to move on to the next. Oh no, sorry. Do we have one more? Yes, Sam. Do you want to ask something quickly?
Yeah, so I just wanted to follow up very quickly. So you said the LSTM network outperformed other simpler ones. I'm just curious, outperformed under which metric? Sort of what did you use to score the performance of each of the things you tested?
The score we tested is actually we adapt the training data, the testing data set with the 1 week before the matching week. So the score we set is how close they are. Is also the how do I present it? It's also the error between the predicted and the real PV output and demand data.
Was it like a RMSE or something, or a MAPE?
MSE, I think.
MSE. Okay, brilliant. Okay, yeah, we're going to move. I'm just going to ask anyone who's not presenting, could they turn off their cameras during the presentation? David, I noticed you've got your camera on. Just helps to focus in on the talks. Yeah, so Eugenio, if you would like to give your presentation. So Eugenio is from the EnJoyChAnGe team. They're based at Swansea University.
Okay, great. Thank you for the introduction. So let me find this. Can you see the presentation?
Yes, I can see it. Thanks.
Okay, great. So, before, thank you to the organizers of this very interesting challenge, and congratulations to the rest of the teams. So, yes, I am Eugenio. I'm here to present the main points of the solution of our team EnJoyChAnGe from Swansea University, formed by Cinzia Gianetti, Jay Flynn, Grazia Todeschini, Alma Rehat, and myself. So, okay, by now we all know that we are facing a constraint optimization problem under uncertainty, but more specifically, it is a stochastic second-order comp program. This is related to the constraints being linear and the objective function being quadratic and the decision variables. And what it means is that if we actually knew the demand and PV power generated for the next week, we could actually solve this problem effectively most of the times using just a free available solver. Sorry, I'm not. Okay. And so this forms the basis of our general approach, since it allows to break down the problem into main stages, where we we first predict the PV power and the energy demand for the next week using several different machine learning models. Then we feed these predictions to the optimizer, and the optimizer then outputs the optimal schedule according to the information it receives. Then we have a kind of post-processing step in which we smooth the battery charging profile to generate the final solution. I will explain this later on. So the main thing, the first point I would like to highlight is how we validate our approaches. We use a technique called work-forward validation, which is kind of cross-validation in the area of time series forecasting. So essentially, we used for each challenge week, we used the previous 4 weeks. We run our models 4 times in the way illustrated by the diagram. And then we used the performance of our models in these 4 weeks to choose or to select the best models, to select the best combination of features, to select the best tweaks for each task. And so very briefly, why have we restricted ourselves to 4 weeks? Well, we mainly look at this plot, which is the autocorrelation plot for the demand. We see peaks every 24 hours as expected, and there are also local maxima at 1 week intervals. but these local maxima are decreasing as we increase the lags. So we decided to make a cut here around 4 weeks to get a balance between having a relatively big testing set while retaining characteristics that are similar to the target week. Okay, so regarding the forecasting tasks, well, I will be maybe briefer than the other presentations. For the demand prediction, we used the historical demand data available, joined with the weather reanalysis. We simply linearly interpolated this forecast weather data to half-hour frequency. We added bank holiday dates, the lockdown period, and we engineered several features, which are mainly rolling statistics over the past week for the demand values, some time-related features, such as hour of the day and day of the week, also the cyclic versions of these features, some lagged features, which is just copying previous demand values, and trends, which means, for instance, we took averages of the temperature across different time spans to capture shifts of trends in temperature at different scales. So with this data, we trained mainly 3 models: a cat boost, which is also a gradient boost based on decision trees, a rather flat feed-forward neural network, and a model called TabNet, which is also a neural network that is specially designed to deal with tabular data. So a quick glance at the comparison. We have here a table with the scores in terms of R-squared score and RMSE. We see that the 3 models are pretty accurate, and they are all similar, with cat boost being the strongest one. And we also can understand from the table, looking at the naive baseline row. The naive baseline means just copying the previous week to predict the demand values of the next week. Well, looking at that baseline, we understand that predicting the demand during the lockdown periods is hard, because the patterns of demand become more irregular. Okay, so moving on to PV power prediction, we found, or we felt we had less room to feature relevant, to engineer relevant features. We simply used the historical PV power data provided, merged with the weather reanalysis data as before. With this, we trained 3 main models: a random forest, an LSTM, and an LSTM combined with a convolutional neural network. And for all 3 models, we tried several configurations of hyperparameters. We tried removing some of the features, especially from the weather forecast features from some locations, different time window sizes, and of course, different number of hidden layers and so on for the architectures of our neural networks. This led to an accuracy in terms of R-squared score of around 0.8 and an RMSE of around 0.35, which doesn't look great, especially in comparison to the accuracy in demand prediction. But as I will show in the next slide, we kind of expected this, looking at the available data. So here in the plot, we see data for the week from task 1. So at the bottom, we have the irradiance measured at the 6 locations, at the 6 weather stations. And in blue, the irradiance measured at the location site where the PV panel is placed. And at the top, we have also in blue the actual PV power generated for that week. And we see that it is very strongly correlated with the irradiance due to physical reasons. But in contrast, the irradiance measured at the locations at the weather stations is not so strongly correlated with the irradiance at the target location. And this is bad, or this is challenging, because all the information we have available to predict the PV power is the irradiance measured at these weather stations. So for comparison, at the top, we also have the prediction of our 3 models, which is not very accurate, but it generalizes in a reasonable way the information that it has available. So with this, I want to tell you that uncertainty was we found that uncertainty was one of the main challenges inside this problem. So to deal with it, we mainly adopted 2 strategies. One is very classic, if you want. We considered, and we assembled our models. For instance, you can see in the table that the average of our 3 models for demand prediction is attains the strongest performance. This performance is like an overall. We took the complete data set to make these computations once the challenge finished. We also did something similar with the PV power for the 3 models we had. We averaged them, but we found that the most important thing regarding counteracting the uncertainty in PV power prediction was this kind of smoothing post-processing step I mentioned at the beginning of the talk. So you can check the formula, but what they really mean is that after we get the output of the optimizer, we take the total amount of battery of charge that is prescribed by the optimizer, and we try to evenly split the charge in the different hours of the day, trying to respect the forecasted PV power generation for every time. So maybe it is better explained looking at these 2 plots. So here we have the results for tasks 2 and 4. And in orange, we have the battery charging profile, the proposed battery charging profile, which is generally this kind of smooth bumps. And in blue, we have the actual PV power generated for these weeks, which was not available at the time of generating the battery schedule. And well, so we see that the battery charging profile is smooth as opposed to these blue curves, which are full of peaks. And also in general, the profile, the charge happens is lower than the PV power generated, and this is good because it allows to take advantage of the solar energy produced. Okay, so to close the talk, I would like to mention a couple of ideas that we didn't have the time to implement during the challenge. The first one is, although we are happy in the way this rather ad hoc strategy worked for the PV power prediction, we would have liked to incorporate something that was mentioned by the other participants. We would have liked to include hybrid physical modeling for the PV power generation, because we know that there are equations relating the temperature at the surface of the panel and the irradiance to the PV power generated. And also we would have liked to infer the irradiance at the location site using geostatistical interpolation methods, such as gridding. And regarding the demand prediction, although our prediction was in general accurate in terms of RMSE, we found that somehow it was more important in terms of the challenge score to follow the shape of the demand curve. This means that it's more important to have or it's better to have a steady error, even if it is not a low error, than having a very accurate prediction in most of the times, but with relatively large errors in some point. Okay, so with respect to this, we were able to train up the models in our final task according to a different loss function, but it would be interesting to find the optimal loss function to train the models according to the challenge score and to backtest the strategy across the whole dataset to see how it would have performed. Okay, so we already have a paper on this approach, and thank you very much.
Brilliant, thank you very much. Yeah, so thanks very much. Yeah, is there any questions for Eugenio? I have a quick one. You did, obviously, it's great to do the combination of the methods at the end. Sort of, it's the classic technique to sort of improve things. Did you try any other sort of averagings or weightings, or did you ever think about that? And did you think about other methods you could have put into there to help sort of that combination?
Yeah, so we thought that since we only had three main models, we thought that averaging was our best solution. But yes, at some point we considered like having, for instance, the cat boost, training with different random seeds on small variations of hyperparameters to have a lot of models and perform like most complex ensembling techniques. But yes, we didn't have time to do this. Thank you.
Yeah, there was a tight timeline anyway. Question from Petra Gronat. Is the Conda release part of the paper published? So I guess, is it the code released? Sorry, the code, I think, yeah.
Yes, yes, not great question. And not so far, but we aim to publish the repository, although upon request we could share the code. So it's not very tidy at the moment, but yes, it's an objective.
Brilliant. So yeah, get in touch if you want the code. Another request was about the reference paper, but I think your colleague has actually shared that. So that's open. That's open source. That's open access anyway. So that's free to read. So that's brilliant. Yeah. Any other questions before we move on? Oh well, brilliant. Thank you very much. That was really interesting.
Thank you, Steve. Thank you all.
So the next talk is from the runners-up in the competition. This was the CountingLab team. So this is Colin Singleton. Will give the talk. So he's from CountingLab. They're a University of Reading spin-out.
Thanks, Steve. See if I can share this. Is that working?
Yeah, I can see that.
Great. Okay, good morning. So as Steve says, I'm the technical director at CountingLab. We're a small spin-out company from the University of Reading. We are experts on what we call translational data analytics, which is sort of creating, translating, developing, and applying the latest techniques from academia or other published resources, research houses, into commercial solutions to solve real-world problems. We're sector agnostic. But we typically work in energy sector or defence and security or retail and their suppliers. And, we're happy to use any technique that's out there. We do a lot of segmentation work. We do a lot of regression. We do a lot of deep learning and AI. We do a lot of social media analysis, network theory, and of course we do forecasting. So to talk today, so apparently I did a little bit better in the discharge than the charging profile. So I'm going to focus. Unlike the others, unfortunately, I'm not going to talk too much about the generation aspects, but I'm going to talk most on the discharging aspects of the talk. And what I've got a confession really is that I didn't do anything particularly technically sophisticated. So instead of talking too much about the technical details, I'm going to focus more on the general approach and the big picture. So here's a quote often misattributed to Einstein. It says basically, if I only had an hour to solve a problem, I spend the first 2/3 of that attempting to find and understand what the problem is. And I think all too often we get given a problem, we think, oh, it's all forecasting. We know how to do forecasting, we get stuck into the technical details without necessarily thinking about what the problem is or what is the big picture. So for this particular challenge, there's two potential approaches to defining the discharge profile. One is to directly model the discharge profile. The other is to do what most of the teams have done, is to produce a demand forecast, and then from that forecast of the demand, infer what the optimal discharge profile should be based on that forecast. The first of these allows you to optimize directly the solution, but the latter, of course, allows us to take advantage of all our built-up history of knowledge of how best to do forecasting. Okay. However, so the question here, which forecast is better? Okay, so you've got forecast 1 on the left, forecast 2 on the right. Hopefully you can all see that. In the orange is the forecast. So in forecast 1 and forecast 2, what we've done is taken the average of the previous 6 weeks. And then in the blue is the actual demand. So I don't know if you can see it very clearly, but if we look at the results, forecast 1 is obviously better. It's got lower RMSC, it's got lower MAP, so it must be better, right? Well, actually, the question is ill posed. So I presented the question, I said, which forecast is better? But I didn't actually say what I meant by better. So each forecast could actually be better than the other, depending on what the challenge is. For most applications, forecast 1 is better. However, for this problem, this is what Eugenio was alluding to at the end of his last presentation. Actually, in this particular case, forecast 2 is better because, as Eugenio said, it matches more aligned to the shape of the actual demand data than forecast 1 does. So down here, you can see the little table. You can see forecast 2 has got a worse RMSC, it's got a worse MAP, but actually it does better on the peak reduction. I'll go back to that previous slide, sorry, so you can see again, the actual overall is worse in terms of its fit, but it more closely matches the shape of the demand profile. And so thinking about that, you can see here that this is the actual discharge profile from the different things, and you might be able to see that the forecast 2 is slightly better. Okay, so it doesn't matter so much, as Eugenio said, if the forecast is inaccurate, as long as the inaccuracy is consistent over the discharge period. So if you forecast 1 megawatts too high for every half hour of that day, exactly 1 megawatt hour, you'd actually get an optimal solution for the discharge profile. So what error metric did we use? Well, what we did was the relative forecast error over the discharge period. So effectively, it doesn't matter at all how bad your forecast is outside that discharge period, outside that evening period that you're going to be discharging. You can be absolutely completely out of there as long as in the discharge period you're accurate. And actually, it doesn't really matter, as I've said, if you're actually out overall by 1 megawatt, as long as you're consistently out by that amount. So what we did was, or what I did was, the error metric I used instead of the normal RMSC is I looked at the accuracy for each half hour relative to the 6 p.m. peak forecast. Obviously, not necessarily the peak didn't always happen at 6 p.m., but I consistently did the forecast relative to the 6 p.m. forecast. And then repeated that for the actual ground truth, and then I took the RMSC between the relative forecast and the actual relative. Okay, and this gives you a wide equivalence class of optimal solutions. As I said, if you're out by 1 megawatts above or below, or any amount, but consistently out, you could still get an optimal solution. Okay, there's an excellent paper written by our host today. I recommend you all read it. So it never harms to grovel to the host, but this is really sort of gets you thinking about, rather than just plowing in with your standard RMSC error metrics, thinking about actually, are I using the right error metric for the problem at hand? So it's definitely a paper worth reading, even though it's a few years old now. So a little bit on the technical details of what I did. As I said, there's nothing sophisticated. In fact, everything I did could be done in Excel if you wanted. It's not always as quick to do in Excel, but it could be done in Excel. First and most importantly, I think I cleansed the data. So there was a lot of missing data for the demand profiles. There was some that was clearly dodgy. It was, it was several megawatts too high. And then having done that, I simply really used a weighted average of the previous 6 weeks and then made a small adjustment for forecast temperature. So it's really simple. I didn't have a lot of time to do anything more sophisticated, to be honest. But by using the relative error metric that I used, it really helped to mean that even a relatively simple method provided very good results. How did I get these weights? Well, basically, I calibrated the weights for each of those 6 weeks. So I didn't just use a simple average of the previous 6 weeks. I used a weighting. And then that was based on, optimizing this relative RMSE error. And then I also calculated a separate linear temperature coefficient for each half hour, because I was focusing in on getting the relative half hour to half hour right. So if you remember, so rather than using a single temperature coefficient, which you might do normally, or some more sophisticated technique, I was really just looking at each half hour within that discharge period. There's only 11 half hours we were worried about, and a separate temperature coefficient. So I could really focus in on getting the relative demand correct. The temperature was just calibrated against the 6 weather stations, again, optimizing for this relative RMSE error. And then I also, another thing I added in was a simple coefficient of the day number. And we're going to get too many degrees of freedom if I tried to do it for every half hour. I wouldn't be able to get that robust. So instead of doing for each half hour, those 11 half hours, I split it into an early peak and a late peak. And I had a sort of a separate coefficient for the early peak and the late peak for a trend over time. And then basically what I did was, having done that once, I then looked over the data and I looked to see where was I doing well, whether I wasn't doing well, and looked to think about, is it because my forecasts are inaccurate? Does the method need change, or is the actual underlying data on that particular period something funny is happening? Maybe there's an event going on, maybe there's a misreading in the data, some error in the sensor, maybe there was a power cut, or anything that might have happened that might have affected the data. And in those situations, I replaced the data, the real data, with my estimates. Now, if all this sounds quite subjective and a lot of sort of almost guesswork to you, you'd be right. And so a little quick digression here on subjectivity. So a little of a rant, so you can switch off if you like. But years ago, like, too much data analysis always lacked objectivity. There's always people just put their thumb in the air and guessed, or use their gut instinct. But nowadays I feel the opposite is almost true, and that often we're just focusing in on sort of a prescribed approach that lacks the sort of subjectivity, what we like to call expert judgment, really. And sometimes the computer doesn't always know best, and sometimes actually a little bit of expert judgment does help. So here's a quick example. So a decision scientist comes up and says, look, how's it going to forecast by 10% next year? And a Sparky's sort of junior data scientist overhears this. He wants to impress, so he goes away and he spends months, weeks and weeks refining some, sort of LSTM method and getting all these ensemble methods together. And he manages to forecast that the sales will actually fall by 11.34%, plus or minus 0.2%. Now the problem here is that while that's marginally useful, a much bigger question, which is what the decision scientists will be addressing, is why are sales falling and what can be done about it? So often the prescribed objective approach doesn't always give you the right answer, best answer, because maybe somebody knows best, like COVID's happening, you need to worry about how lockdown's going to impact things, and you've got no history of that, so you've got no history to know what you're going to do, so you have to use expert judgment at that point. But also, often the prescribed approach doesn't necessarily address the real question that's being asked, or actually the question that should have been asked in the first place. And more from a sort of a selfish point of view is that the prescribed approach is being taken over or run more and more by automation, or by low-skilled work also can just use some already built-in Python library or whatever it is. And so it's my feeling that actually if we carry on down that route, then we might all be unemployed. The only people who will be employed will be the senior ones who are able to take those sort of more senior expert judgment views. So sorry for a little rant there, but I think we should sort of often sort of focus in on objectivity a little bit too much. always remember the big picture. Quick go on the PV charging profile. So as I said, I didn't do as well on this. Don't want to spend too much, but I basically used a Bayesian linear regression to estimate the relationship between solar luminosity and power. The prior there was the whole history of data, so basically a multiple linear regression between the whole history of data of solar PV estimated and the power, and then that was updated using the most recent weeks and the period of time around the same time previous year and the previous year before that, for example. And then what I wanted to do is take two extremes. So either I found we had far too much PV anyway, so we needed to just make sure that every half hour we're getting as much as possible, or we didn't have enough. So depending on those two regimes, I took the other, the steepest slope or the most shallow slope. I also formed an average from a similar period of time, so the recent couple of weeks and the serious time over the last few years. So my idea here is the first one gives you an uncertainty on the relationship between the luminosity and the battery charging, while the second one gives you an uncertainty around the actual forecast in the first place. So if the forecast is wrong, then the average from the previous few days and previous similar time previous years at least should be roughly right. And then I interpolated on the two, between the two, depending on, as I say, which regime we were in, whether we had excess PV or insufficient PV. So that's pretty much it. And finally, I just wanted to mention a technique that sort of seems to be becoming more and more popular. Nobody's talked about it yet in any of the talks so far, which is called multivariate singular spectrum analysis. And you can really think about this as a principal component analysis for time series. It allows you to sort of decompose a time series into various components which typically have a meaning. So there might be sort of a seasonal trend, a recent trend, might be noise, and things like that. So as opposed to like whole winters where it's very prescribed what the decomposition is, here it's a data-driven decomposition based on the lag covariance matrix. So yeah, so that's pretty much it for me. Short and sweet.
Brilliant. Thank you very much. That was an excellent talk, not just because of the shout out. But yeah, that was really interesting. So yeah, first, have we any questions for Colin? I have a quick one actually, which I think. So you mentioned, I mean, there's a lot of data-driven stuff in there, even though there's a lot of judgment as well. What's stopping you sort of? I mean, you said that actually just creating a forecast for the method, maybe not the, just an accurate forecast might not be the best thing to do. You want the best forecast for the method. So could you not have solved the entire thing just by solving the battery optimization and finding the best schedule? I mean, that's a full data-driven. Could you talk about that maybe a bit?
Yeah, so that was the first option. I don't know if you remember my second slide. I said there were two approaches. Yeah. We could either directly model the discharging profile, or we could do this sort of produce the demand forecast and the PV forecast. So, potentially you could just say, we've got for every day of the week, we've got half-hourly numbers that we want to put into the discharge profile and the charging profile, of which most of those we know will be zero because they're overnight or whatever. And you could use an ensemble algorithm that just says, these are my target numbers, basically those charging and discharging numbers, and feed in all the input data that you would feed in. And you can use any of those sort of general learning algorithms, gradient boosting machines, for example, to actually say what is the optimal charging or discharging profile, rather than splitting it into two different tasks. But as I say, there's less history in that, so it may or may not be as successful.
Is that why you didn't try it, or?
I didn't try because I didn't have time to.
Okay, so we have so there's a Simone Blackburn shout out here, loved the talk. And the second, Brian Collins asked about recommended paper, maybe reference paper for the technique you mentioned at the end, the multivariate singular spectrum analysis. I guess you could put that in the chat.
Yeah, I'll have to
Find
dig
something?
one out and have a look and see what I can find.
That'd be really good. Is there any other questions? If not, then thanks again to Colin. That was a really brilliant talk. And we have the final talk of the day then. So Cameron, yeah. So the final talk we have is from Team Cameron. So this is just Cameron Roach on his own. I guess you were a PhD when you were doing this at Monash University in the forecasting, I believe.
So
close to it.
Sorry, I haven't given a good background. My background is I did a PhD focusing on similar things. That was a while ago. This is just something I did for a bit of fun. So I had a bit of time spare over the Christmas holidays and decided to work on this. But yes, I've worked at the Australian Energy Market Operator, looking at peak demand forecasting, and also worked at a smaller company, Buildings Alive, looking at energy analytics in commercial buildings. So yeah.
Brilliant. Thank you. So take it away.
Great. Can I just check? I've just gone full screen with these slides. Are they still showing, or has it disappeared?
No, they're showing. Yep.
Ah, fantastic. I'm just going to do one more thing to make sure it's still working. I'm going to go to slideshow.
I should say as well, congratulations on the first place prize as well. So
oh, thank you.
And the winning method.
Well, thank you for putting it all together. It was a lot of fun, but I'll jump into it quickly. I'll try and keep it short and to the point. So this presentation is just going to talk about the solution I used. I'm going to talk about the training data, some of the feature engineering I did, the various forecasting models I used, and the eventual scaling methodology I used for the battery. And I'll just I've put a short example in at the end just to try and make everything nice and clear. So first of all, I just wanted to talk about what data was used. There were a few different sources. We had electricity demand data, which served as one of the response variables for one of my models. Similarly, we had solar PV generation. We also had reanalysis, temperature, and irradiance data for all 6 locations. One important point to mention is that there was solar irradiance data and PV module temperature that was available at the site of the solar farm, but there was none of this data included in the horizon, so I decided against using that data. One point to note is that the reanalysis temperature and irradiance data was supplied in hourly values. So similar to what other teams did, I just linearly interpolated those values to get half hourly values. I didn't want to spend too much time on that. After spending a bit of time thinking about how to go about this, I settled on focusing on forecasting. I put a lot of effort into making sure that my electricity demand and PV generation forecasts were going to be okay. After that, it was reasonably straightforward, actually pulling a battery schedule together. For my charging schedule, I simply looked at scaling the PV generation forecast. I didn't do anything too fancy there. I just wanted to scale the PV generation forecast to make sure that I was charging less when there was less PV generation needed and less PV generation being produced, and charging more when there was more PV generation being produced. So nothing too wild there. And as for scheduling the battery discharging, I actually just came up with a closed form equation to work out what the discharging schedule should look like, because obviously if you're minimizing the peak, you want the evening demand to be completely flat. So assuming you've got good forecasts for your electricity demand, it's reasonably straightforward to come up with an equation to give you your schedule. So I'll quickly talk about those things. The electricity demand model was trained only on data demand that occurred between 3:30 p.m. and 9 o'clock p.m. I removed 3 dates that were pretty obviously outliers. You can see in this plot here, this is showing the evening demand for every day in the historical data. 3 of these outliers were removed. You can see some of them just look clearly strange. For the model, I simply trained gradient boosted decision trees implemented using light GBM. There was no magic reason I chose light GBM. It was simply because I've heard it's a really, it's had a lot of success in data science competitions, and I just wanted to use this as an excuse to learn something new while participating in the competition. More importantly, I think, is the feature engineering that happened. So these are the features that I used when I was training the model. I decided to focus on building a highly parameterized model where I had lots of different variables. I had calendar effects, had half-hour, period of day, day of year, day of week, public holidays. But then I also included a lot of lagged variables. So for instance, I included demand lagged by 1 week. I experimented with a lot of different lags to see what worked and what didn't. I also included temperature and solar irradiance lags for all 6 of the reanalysis locations. The previous day's maximum, minimum, and average temperatures across all 6 reanalysis locations were used. And then I also included a trend variable, which was very useful during the COVID period, because it was just a number that went from 1 to the number of dates of data I had. And that was just a way of picking up any trends that were occurring. Because this was such a highly parameterized model, I needed to make sure that I wasn't overfitting. So similar to one of the earlier presentations, I used time series cross-validation to tune the number of leaves and learning rate parameters. I typically used, I was using week-long folds to mimic what was happening in the competition, and I just picked, I picked 5. There was no real science behind that. It just seemed like a good number. Then I would typically create a grid and see which performed well. I used RMSE here as my metric. I also experimented with mean absolute error. I didn't stress too much about this because I saw pretty similar results regardless of which metric I was using. With the benefit of hindsight, I wish I used the competition's metric, because that would have obviously made a lot more sense. But it worked well enough for picking a suitable set of hyperparameters. I used a similar approach with the PV generation model. Again, gradient boosted decision trees implemented using light GBM. Originally, I was only producing point forecasts, but towards the end of the competition, I started experimenting with quantile forecasts. The idea there was, I figured if I was forecasting quantiles, I'd be able to see what the different shapes of the PV generation, I'd be able to see what the distribution of the PV generation profile would look like. It didn't really make much of a difference to the performance, but that's something I want to experiment with a bit more down the line. Again, probably more importantly, the features I used here were a half-hour period of day, the month of the year, the day of the year, and temperature and solar irradiance variables with lags for the last 6 half hours. So again, highly parameterized, use time series cross-validation again to sort of test which hyperparameters worked well and ensure that some form of regularization was taking place. To schedule the battery, I simply just scaled down whatever PV prediction I chose to ensure it summed up to 6 megawatt hours over the allowed charging times. That seemed to work really well, and there was no penalty for importing from the grid, so I wasn't concerned about this. I was always happy to fully charge the battery, even if some of the power was coming from the grid. Now, when it came to discharging, I realized I could come up with a closed form equation for what the battery discharging schedule should look like. So given that I wanted my eventual profile to be completely flat, I called this, this demand L star D. And I realized that if you just summed up all of the forecast load values over the period of over periods 32 to 42, it was going to be equal to this new peak multiplied by the number of periods that we would see this peak happening over, plus 12, which is just 6 megawatt hours converted to megawatts happening every half hour. And then just rearranging that, you get a formula. One once you have that formula, it's very straightforward to obtain your battery discharge values. It's just the difference between this new peak L star D and the forecast demand values. I also had several checks in place to make sure that the battery constraints weren't being violated. In the end, it didn't come into play. The magnitude of the charging and discharging values were always less than 2.5 megawatts, but there were a few little checks in the code to make sure that was okay. So I'll go through an example now, which will hopefully make everything a bit clearer in case that wasn't as clear as it could be. Here's a example. This is just one of the days, I think, from the last week the last week of the competition. We can see a pretty standard electricity demand profile. PV generation jumps around a little bit, but there's still a lot of it. So the first step was to produce a PV generation forecast. This is nice and smooth. I'm pretty happy with it. It's not jumping around a lot, which would make me concerned that there was some overfitting going on. I'm happy with that. Then I simply scaled it down over the charging periods. These bars here all sum to 6 megawatt hours. Following this, it was a matter of just forecasting the demand over the evening period. Using that formula I showed before, I could calculate this blue line here, where I wanted the reduced demand to get to. And taking the difference, I arrived at my discharging schedule. So how well did this work in practice on this particular day? We can see what it would look like. The red line shows the original demand. The blue line shows what the reduced demand would be. And obviously, this was just for the competition. In practice, we might not want it to go that low, maybe. Maybe we want to spread it across the morning period as well, or have a wider discharging period. We could do a lot of different things, but there's definitely scope to experiment and improve on it. Yeah, so that's the basic idea. All the code is, I was writing it as an R package as I went. It's all available from my GitHub repo, which is listed here. And the code for this presentation is available from here as well. So yeah, that's basically it. Thank you.
Brilliant. Thank you very much.
No worries.
So I've just put your GitHub link in the chat, if that's all right. Then
no stress.
Shared that. Yeah, that was great. Did you find? So I got a quick question. So yeah, please put again any questions in the chat. How much did you change what you did from one week to the next? I guess is the first question, and how much do you think that affected what the results?
So there was a big change between the practice round and the first round, mainly because in the practice round, I just built a benchmark model, which I think was probably pretty similar to your benchmark model. I just wanted something quick and easy that I could assess anything that I made against. I thought that was very important to have. So big change actually moving towards, moving from the benchmark model to the final competition model. There weren't huge changes mainly because I tried to be very disciplined, and every time I came up with what I thought was a great idea, I'd always test it, and more often than not, I found out my ideas weren't as great as I thought, and so it didn't evolve too much as I went through it. I was always trusting the cross-validation, and I was trying to minimize the amount of data leakage that was occurring. One thing, I think the biggest change was moving towards the probabilistic forecasting for the PV model, but that opened up a lot of questions. I wasn't quite sure the best way to go about fitting the model once I moved towards a probabilistic model, because obviously you can use quantile loss scores or pinball loss score or whatever you want to call it. But the question was, do I want to assess the whole do I want to assess all the quantiles? Do I only want to assess the quantile of interest that I choose for discharging? Do I want to sort of go back and forth between the whole distribution and then picking one and then tuning it and going back? It got very computationally, it was going to be computationally expensive. And I was also doing this on my old MacBook Pro, and I didn't want to spend much time waiting on it to complete. So yeah,
I guess it links back to what Colin was saying in terms of what's best for the schedule in the end, isn't it?
Yeah.
rather than what's purely accurate. There's a quick question that came in the chat first, and then we'll get Robbie to ask a question. Mark and Linda sort of linked their question really there. It's about you said you were happy to fully charge the battery. Were you happy with that by the end of the competition? And then Linda sort of says, because yeah, you if you charge from the grid, you can impact the score if you don't get fully PV.
Yeah, totally. And that's why it was important to try and schedule the battery charging so that I was pulling in more charge at times when I was predicting a lot of PV generation to happen. Obviously, how to explain it? There were some days where my PV forecast would be quite spiky. And so I'd obviously be scaling that down and trying to make sure that I'd try and charge from those points when there was going to be more PV generation. However, if I happened to be wrong with my PV forecast, I'd still rather be charging the battery because that would have had a bad impact on both the score for the amount of charge I got for the battery, because I still got a higher score even if I charged from the grid. But it would also have had a bad impact on the amount I would have been able to reduce the peak as well. Sorry, I don't know if that explained it very well. Basically, I wasn't concerned.
Yeah. No, is the answer not. So yeah, Robbie, do you want to go ahead?
Yes, I'm interested in getting some of this information out and into the more general energy system models. So my question is, can some of the battery scheduling policies be described for use in perfect forecast models, or even some of the simpler forecasting techniques be used for stepwise models? I'm just trying to get some technology transfer going.
I'm not sure I understand the question.
Well, you have a class of models out there which are that look forward 30 years and examine decarbonisation trajectories down to net zero, and they take simplified representations of all sorts of things. I just wondered if some of your work can be exported to them.
I don't know off the top of my head. I'd have to have a look at it. If you want to send me a message or an email or something like that, I can do a bit of reading and maybe look into that a bit more. But off the top of my head, I really don't know how well it would transfer to these other models because I'm not familiar with them.
Yeah, this is a general question for the other teams as well, or for the general project.
Yeah, it's an interesting point as well. Yes, so if anyone has any other sort of comments on that, I think definitely get in touch. And Robbie, you're part of the open mod community.
Absolutely.
Which is interested in. I think also what you're mentioning there is we're talking about longer term models are often very smooth, aren't they? And I think obviously the models here we're dealing with are kind of operational. So it's about translating, I think, something that's operational into something which is a long-term model, which is smoother. You somehow have to model the uncertainty correctly. So if you can do that, then definitely you can model that in there. That would be the off the top of my head sort of thought about that.
Can I pick you up on the smoothness? Now, our models aren't smooth. They're full of what you might call network effects, where a line capacitates and a new power station comes online. You'll know from the NEMO, the market stuff that you're doing in Australia that these systems jump all over the place under so smooth is not a correct characterization.
Yeah. Okay. Yeah, I think you're right there. What I'm and please anyone else jump in here. There's there's sometimes a bit more of a higher level modeling, and getting a longer term model to have the right interdependencies and some of the features is a bit tougher. So I think it's not unheard, and I think we do a bit in the Energy Systems Catapult looking at sort of modeling those things. But getting that, I think it's been mentioned to me, is sort of the veracity of nature to get that reality in there. To know that we can do something operational. So if you look at all the models that have been coming on here, you have people using autoregressive features. You're learning from the recent past. So you've got to have that to learn from make it realistic in that sense. And they're purely operational, I guess, in this place. But yeah, I think with a bit of work and quite a lot of assumptions, I think maybe.
Yeah, it might be possible, but again, it's something where I'd have to look at it carefully to give any sort of confident answer, because I'm not overly familiar with the models you describe.
But definitely get in contact with each other. I think,
yeah, please.
Happy to connect anyone up who wants to chat further after this, if everyone's happy to, for me to introduce them. I guess I have one more question, and then maybe we can open the floor up and have a bit more discussion. Yeah, so Cameron, so actually talking about those features you used in the past, they seem to be really important of how well a method does, and I think that's maybe across the board, across all the approaches. Like, how did you go about that, and how do you decide that a feature is important, or to include in there?
Yep. The initial batch of features I used were informed by what I've seen work well in the literature in the past. There have been quite a few forecasting competitions that focused on energy and variables that captured effects such as thermal inertia or day of week effects, stuff like that. That's all reasonably well established. I more or less just picked a few that I thought would be useful, and every time I wanted to use a new variable or test something that I thought would be a good idea, I always made sure that I carried out cross-validation, checked if it was going to actually improve things or not, and then scrapped it if it didn't. And if it did improve things, I'd include it, and that extended to additional lags or removing lags and things like that. I could have used a computationally expensive approach, such as stepwise variable selection. I really didn't want to because I couldn't be bothered. And I feel like I kind of, in my heart, I kind of agree with a lot of what Colin was saying in the previous presentation, where you've got to have some sort of subjectivity, otherwise it takes too long to get things done. You just need to sort of know what things are kind of going to work initially if you want to get things done quickly. So yeah, so that was kind of my approach. A little bit of subjectivity, and then trying to be a bit more rigorous when after I came up with those initial variables.
Brilliant. Okay, thank you. Yeah, so I guess if there's any other questions, add them in the chat. Or Robbie, have you any yours, or is it just your hand from earlier?
It's up from earlier.
Okay. Also, yeah, I understand several teams, and I think some of them are in the audience today. They also put GitHub pages together, so feel free to share those with their own code in as well. I think this will be going on our YouTube page once we've sort of got it ready and released that. So, but yeah, feel free to get in contact. I just want to thank everybody as well, all the audience, all the questions. The speakers as well for putting together really interesting and diverse sort of ways to approach this problem. I'll just sort of finish off here. Really, I think there's a lot of sort of benchmarks and models out there which are, there's not a lot of testing all the time. The academic research doesn't always have that data out there as well to show. We need the data to sort of test these methods, and we need that data open to do that. And I think that's what the presumed open data was very useful in demonstrating, is getting data out there. Shows not only is that useful for developing these techniques and various innovation, but there's a lot of thirst for it as well, shown by the participation we have. So yeah, I'll probably stick on here for a little bit longer, and maybe if the speakers, if there's just in case there's any other questions, but if not, I just want to thank you all, and have a great rest of your day.